Thank you. Thanks for inviting me to speak today. So I'm at the Joint Quantum Institute, which is a collaboration between the University of Maryland and the National Institute of Standards and Technology, or NIST. And let's see. Yes. What can you see? Am I sharing it with the notes or sharing it with the?
I can just see the first slide, so we don't see the notes.
I don't seem to. Interesting. Did that advance?
Yep.
Okay, great. So I'm a physicist, which means I try to understand the physical world around us. So fundamentally, my job is to try and understand things with the hope that as we understand more about the world and about systems in the world, that we're going to be able to understand the things we're trying to build, troubleshoot them, also just to ponder the mysteries of the world and try to understand things. So specifically, one of the things that I'm interested in is how new properties emerge when you have systems with lots of particles in it. So one example is temperature. One water molecule all by itself doesn't have a temperature, but when you have a whole glass of them, suddenly there's this thing called temperature. Or glass or water or metal or a semiconductor or a superconductor, they're all just made out of protons and neutrons and electrons, but they all behave differently. The glass is an insulator, the water is a liquid, the magnets are magnetic, the metals are shiny, the superconductors, they repel magnetic fields. And I'm most interested in and most excited about understanding how quantum properties of each individual particle in a group combine to make the world that we see around us. So I personally do computer simulations of the physics of many electron systems. I don't work alone. I work in a team of a whole bunch of people, and these are some of them in the atom scale devices group at NIST. Some of them are experimentalists, and they are basically trying to develop new hardware for what will be quantum computer chips in the future. So they're building devices that can trap one electron at a time. And then once you've trapped it, then the spin of the electron, the two possible spin states of the electron, can be the qubit that can hold your quantum information in your quantum computer. So some of them build integrated circuits, which are really similar to the ones that are in your regular computer chip, but the silicon that they build it on has been purified so that the isotopes that will interfere with the spin and ruin your qubit have been taken out. And then they pattern these metallic gates on this special silicon, and they apply a voltage so that it draws the electron in and it can trap it in one small region to hold that electron. Others use the tip of the scanning tunneling microscope to place an atom right where they want it in the silicon. And then the atoms, because their nucleus is positively charged, then they'll be able to trap an electron that way. And then some of us are theoretical physicists. And then we try to predict what interesting effects the experimentalists might be able to see in their system. We try to explain the data that they get. They mostly do that job, but they talk to us to try to understand like what's happening in their actual physical system. And we do this by building computational models of those systems. And what that means as a model is that we're trying to capture the important elements of what's happening, but in a way that's simple enough that we can solve all the equations that predict what will happen. So I mentioned that metals are shiny, and that's actually one of the things that I've worked on to some extent. So a metal is shiny because it has electrons in it that can move around. We say it's a conductor because the electrons carry electricity when they move around. Those electrons are also all negatively charged, and so they repel each other. So they're interacting. So a light wave is an electromagnetic wave. It has electric fields that are changing. If you shine that light on a metal, the electrons move in response to that magnetic field, and they all move together because they're repelling each other. If you push on one, it pushes on the next one. And the movement of all those electrons together generates a new electromagnetic wave that's very similar to the original wave, but it's moving in the opposite direction. And so then you're going to see the same pattern of light that was originally headed toward the metal that's going to end up in your eye. So I wanted to see if I could see that emergent behavior of kind of being able to reflect in some way in a model with only a few electrons. So in my model, I have electrons that can sit on sites that are sort of like those atoms that my experimentalist friends can put in the silicon. And my model just had, to start with, one of the sizes that I worked with was just 12 atoms with 6 electrons that can hop between them. And all the electrons repel each other. They're all attracted to the positive nucleus of the atom. And that's obviously a very simplified model that doesn't capture all of the actual physics that's in a real hunk of metal or even a real simulator that one of the experimentalists builds. But the advantage of that simple model is that I could find the roots of that metallic behavior, because I can use a computer to describe that model, and I can find every single possible state that those electrons could ever be in. If you have 12 atoms and 6 electrons, there's only 924 ways to put those 6 electrons in those 12 sites. And so I can use a computer to solve the equations to say, what are all the states? So this plot shows some of those states, all those blue lines. For every state, this actually doesn't show all of the states, but for every state up to this energy, I made a line. I made a line right at its energy. So the lowest energy state, it's actually over here at 0 and you can't see it. That's called the ground state. And these are all the excited states of the system. And the height of the line is something sort of like how much repulsion energy there is between the electrons when they transition from the ground state into this particular excited state. And so when I looked at all of these states, so the thing about being a computational or theoretical physicist is you write down these equations and you solve them, and then you say, what did that tell me? Now I have a representation in my computer of all those states. How do I learn something from it? And then I have to figure out, okay, how do I learn something from this? And so I make lots of plots. This is a plot of something called the transition charge density. And it's something kind of like how the charges are moving when they go between the ground state and this particular excited state. And what I saw was that there's these different modes that exist. And they look a lot like the different modes that exist in a flute. When you look at the pressure of the air in a flute, these modes happen actually again and again in lots of different kinds of physical systems, whether it's waves on a water, waves on a guitar string. And here they are showing up. And these are the Plasmon modes of this system, of this little, very simple model of a metal. Excuse me. So, so you can see these look sort of like a cosine wave. And so these modes are the roots of the metallic behavior of why a metal is shiny. And they're this collective behavior that comes from the electrons all moving together, just like in the reflection. But I couldn't actually do this calculation for a much bigger system size. I can do a chain of 24 atoms and 12 electrons, and that's actually what these particular results are. But then I couldn't even calculate all of the states of the system. I could if I worked really hard, but it was a lot more work to do that. And I can't really get any bigger than that at all. I need a quantum computer to eventually help me figure out how does this behavior transition from this tiny little system to one that's much bigger. So it's sort of a symbiotic relationship between theorists and the experimentalists and all the people who are building the quantum computer that we're all going to benefit from. So a little bit about my quantum journey. I knew when I was young that I really liked understanding why things happen. And so I chose to study physics. And then while I was an undergraduate student, I became a mother. And I knew that I still wanted to be a physicist. So I talked to my professors and I figured out a schedule of classes that could still get me a bachelor's degree in physics while I was also parenting. And then when I finished my bachelor's degree, I wanted to get a PhD, which is the degree you need to do scientific research. And so I chose to do go to a graduate school that was near my mom because she could help care for my daughter. And eventually I moved to NIST, where I came for a postdoc. That's what it's called when you do research after you get your PhD. And being a single parent in a new state alone was really challenging. My daughter has really profound intellectual differences, and the effect of trying to support her, it nearly cost me my career in physics. And I was really lucky that I had somebody who hired me again after that. And I was really lucky that I have built and continue to have a network of people who've helped care for my daughter. And that's made me a lot more successful in my research. And so I just want to mention Corinne Minot was one of my professors who really gave me a lot of support and advice and helped me figure out how did I stay a physics student. My mom and my daughter, Garnet Bryant, who was that person who hired me again, and my partner, Ryan, who is the biggest component of that research team, or sorry, of that support team who cares for my daughter, who become her father. So there are people all around you who want to see you succeed, and each one of them has something different to offer. We all need support. You're going to need help. You don't know what's the best route to take in your path. And so ask a lot of questions from a lot of different people. Even if you feel different from them, they have a perspective to offer you. And especially when you're not sure of yourself, do I belong in this field? Talk to people. And if it doesn't work out with the first person, ask somebody else. It's okay for you to be whoever you are, and you can still belong in physics. So thanks.